Greetings, I'm Salvador Cordova. Welcome to the college level general chemistry lecture series presented by the Evidence Reasons Academy. This video is the Part C lecture of Section 1.6 entitled Mathematical Treatment of Measurement Results in the Chem 2E OpenStax collection. Thank you for joining me today. To all those who have watched this series so far, I salute you for your commitment to learn. Kudos to all those who endured the previous two parts of Section 1.6. And now let's cover Part C, which is the third and final part of Section 1.6. Conversion of temperature units. We use the word temperature to refer to the hotness or coldness of a substance. One way we measure a change in temperature is to use the fact that most substances expand when their temperature increases and contract when their temperature decreases. The mercury or alcohol in a common glass thermometer changes its volume as the temperature changes, and the position of the trapped liquid along a printed scale may be used as a measure of temperature. Temperature scales are defined relative. Temperature scales are defined relative to selected reference temperatures. Two of the most common used are the freezing and boiling temperatures of water at specified atmospheric pressure. On the Celsius scale, 0 degrees Celsius is defined as the freezing temperature of water and 100 degrees Celsius as the boiling temperature of water. The space between the two temperatures is divided into 100 equal intervals, which we call degrees. On the Fahrenheit scale, the freezing point of water is defined as 32 degrees Fahrenheit, and the boiling temperature as 212 degrees Fahrenheit. The space between these 2 points on a Fahrenheit thermometer is divided into 180 equal parts. Defining the Celsius and Fahrenheit temperature scales as described in the previous paragraph results in a slightly more complex relationship between temperature values on these two scales than for different units of measure for other properties. Most measurement units for a given property are directly proportional to one another, that is, y equals mx. Using the familiar length units as one example, length in feet is 1 foot divided by 12 inches times the length in inches, where y equals length in feet, x the length in inches, and the proportionality constant m is the conversion factor. The Celsius and Fahrenheit temperature scales, however, do not share a common 0 point, and so the relationship between these two scales is a linear one rather than a proportional one, that is, y equals mx plus b. Consequently, converting a temperature from one of these scales into the other requires more than simple multiplication by a conversion factor m. It also must take into account differences in the scale's 0 points, that is, b. The linear equation relating Celsius and Fahrenheit temperatures is easily derived from the two temperatures used to define each scale. Representing the Celsius temperature as x and the Fahrenheit temperature as y, the slope m is computed to be m equals delta y over delta x, which is equal to 212 Fahrenheit minus 32 degrees Fahrenheit, and we divide all that by 100 degrees Celsius minus 0 degrees Celsius, which is equal to 180 degrees Fahrenheit divided by 100 degrees Celsius. So 9 degrees Fahrenheit divided by 5 degrees Celsius. The y-intercept of the equation B is then calculated using either of the equivalent temperature pairs, 100 degrees Celsius, 200 degrees Fahrenheit, or 0 degrees Celsius, 32 degrees Fahrenheit. And now just look at this equation here. B equals y minus mx equals 32 degrees Fahrenheit minus 9 degrees Fahrenheit divided by 5 degrees Celsius times 0 degrees Celsius equals 32 degrees Fahrenheit. Now, I'm going to pause here. I know that looks like a mess. Don't worry about the derivation. Just take the final result, and that's good enough for chemistry. So unless you're really into the math part, you can skip that derivation, that explanation, and just go to right here. All you really need are the conversion factors, or the conversion equation, I'm sorry. The equation relating the temperature T scales is then temperature in Fahrenheit is 9 degrees Fahrenheit divided by 5 degrees Celsius times temperature in degrees Celsius plus 32 degrees Fahrenheit. An abbreviated form of this equation that omits the measurement units is temperature in Fahrenheit is 9/5 times temperature Celsius plus 32. Rearrangement of this equation yields the form useful for converting from Fahrenheit to Celsius. That is, temperature Celsius is 5/9 temperature Fahrenheit minus 32. As mentioned earlier in this chapter, the SI unit of temperature is the Kelvin. Unlike the Celsius and Fahrenheit scales, the Kelvin scale is an absolute temperature scale, which 0 Kelvin corresponds to the lowest temperature that can theoretically be achieved. Since the Kelvin temperature scale is absolute, a degree symbol is not included in the unit abbreviation K. The early 19th century discovery of the relationship between a gas's volume and temperature suggested that the volume of a gas would be 0 at minus 273 degrees Celsius. I actually didn't know that until now. In 1848, British physicist William Thomson, who later adopted the title of Lord Kelvin, proposed an absolute temperature scale based on this concept. Further treatment of this topic is provided in this text's chapter on gases. The freezing temperature of water on this scale is 273.15 Kelvin, and its boiling temperature is 373.15 Kelvin. Notice the numerical difference in these two reference temperatures is 100, the same as for the Celsius scale. And so the linear relationship these two temperature scales will exhibit, between these two temperature scales will exhibit a slope of 1 Kelvin per degree Celsius. Following the same approach, the equations for converting the Kelvin and Celsius temperature scales are derived to be temperature Kelvin, T sub K, is equal to temperature sub degrees Celsius plus 273.15, or temperature subscript degrees Celsius equals temperature Kelvin minus 273.15. The 273.15 in these equations has been determined experimentally, so is not exact. Figure 1.28 shows the relationship among the temperature scales. So let me zoom out a little bit here. So you can see the temperature scales. Excuse me for a moment. Let me get rid of that. Okay, so you could see the Fahrenheit, the Celsius, and the Kelvin scales. So we see the boiling point of water is 212 Fahrenheit, 100 degrees Celsius, and 373.15 Kelvin. We see here that the Celsius degrees between boiling and freezing is 100, and same for the Kelvins, but it's 180 degrees between boiling and freezing for Fahrenheit. And then minus 40 degrees Fahrenheit is also equal to minus 40 degrees Celsius. That's just an interesting data point, which is equal to 233 Kelvin. 233.15 Kelvin, excuse me. So that was figure 1.28. And now I'm going to just expand, go back and expand so we can see the text. Although the Kelvin absolute temperature scale is the official SI temperature scale, Celsius is commonly used in many scientific contexts and is the scale of choice for non-science contexts in almost all areas of the world. Very few countries, the U.S. and its territories, the Bahamas, Belize, Cayman Islands, and Palau, still use Fahrenheit for weather, medicine, and cooking. Example 1.11, conversion from Celsius. Normal body temperature has been commonly accepted as 37.0 degrees Celsius, although it varies depending on time of day and method of measurement as well as among individuals. What is this temperature on the Kelvin scale and on the Fahrenheit scale? So this is the solution. You take, so Kelvin equals degrees Celsius plus 273.15. So if the temperature in Celsius was 37, we just take 37.0 plus 273.2, and that equals 310.2 Kelvin. And in Fahrenheit, what we have to do is take 9/5 degrees Celsius plus 32, so that's 9/5 times 37 plus 32, and that equals 66.6 plus 32.0, and that's 98.6 degrees Fahrenheit. Now you'll notice here they dropped the units just to make it's really a shortcut. Technically that's not exactly correct, but as long as you get the right units in the end, that's okay. So now let's check our learning. Convert 80.9 degrees Celsius to Kelvin and Fahrenheit. Okay, so now it's time to check our learning. Convert 80.92 degrees Celsius to Kelvin and Fahrenheit. Unfortunately, I already showed the answer, but let's just, for this sake of practice, I'll just conceal the answer for right now. So to do this, it's not too hard. When you're going from Celsius to Kelvin, we just use this approach. You take the Celsius and then you add whatever figure that is and add 273.15 to it. So when I did that, let me show it here on the spreadsheet. You could see I took 80.92, added 273.15 to it, and I got 354.07 Kelvin. And I just checked the answer that it is correct. And then now let's try to convert 80.92 Celsius to Fahrenheit. So what you do is you take the amount of degrees Celsius and multiply 9/5 by it and then add 32. So 1.8 is 9/5, and then I multiply this number, I multiply degrees Celsius by 9/5. And that's easily done in a spreadsheet. I could just, that's why I really recommend learning how to use a spreadsheet. I can just do that multiplication there, and then I add 32, and I get, without accounting for significant figures, 177.656. Now, since the original number that we're trying to convert from Celsius to Fahrenheit is 4 significant digits, and you remember hopefully how to compute the number of significant digits, and that is 4 significant digits, so I just round that to 4 significant digits. And so that should be 177 degrees Fahrenheit. 177.7 degrees Fahrenheit. So let's check the answer. And the answers in the answer key are 354.07 Kelvin and 177.7 degrees Fahrenheit. So that's very good. Let's continue. Conversion from Fahrenheit. Baking a ready-made pizza calls for an oven temperature of 450 degrees Fahrenheit. If you are in Europe and your oven thermometer uses the Celsius scale, what is the setting? What is the Kelvin temperature? So the solution is we take 5/9, we take the Fahrenheit and subtract 32 from it, multiply by 5/9, and just crunch the math through, and you get 232 degrees Celsius. Now, that looks like it's only the original temperature in Fahrenheit was 2 significant figures, so, and it says here use 2 significant figures, so that would be 230 degrees Fahrenheit. Now to Kelvin, it's very easy. We just add 273.15 to the degrees Celsius, crunch through the numbers, and we get 503 degrees Kelvin. And since we want 2 significant figures, it should be 5.0 times 10 to the second power Kelvin. So 5.0 is 2 significant figures. That's using scientific notation. So now let's check our learning. Convert 50 degrees Fahrenheit to Celsius and Kelvin. So the first thing to do is we can convert the Fahrenheit here to Celsius. Let's do that first. It's not too hard. We have the example right here. So the first thing to do is to take the degrees Fahrenheit and subtract 32. So on my spreadsheet I'll just do that. Like that. And then we multiply this result here, and maybe I'll color it. Is there a... Maybe I'll color it. I'll multiply that result by 5/9. So in a spreadsheet this is really easy. And I get 10 excuse me. I get 10 degrees Celsius. Now there's a little subtlety here. Do we want to say this is 2 significant figures or 1? I'm just going to make it 2 significant figures. There's a way it could have been done in scientific notation to make it really explicit that it's 2 significant figures, but it's just a little awkward to just make it only 1, because we know a lot of thermometers are capable of 2 significant figures. So I'm just going to assume here 2 significant figures. Significant figures. I'm just going to assume 2 significant figures. Then the results will look a little better. So all I have to do then to calculate the number of kelvins is I just add 273 to the Celsius figure. So that's easily done. 273, actually it's 273.15. We get 283.15, and to 2 significant figures, that's 280 280 Kelvin. So let's check the answer. And let's compare it. So the number of Celsius is 10 degrees Celsius, and the number of Kelvin is 280 Kelvin. And that's it for part C of this section, section 1.6, mathematical treatment of measurement results.